My name is Somashekhar, course faculty for this course. Correct, friends? Now I will solve some of the simple numerical problems for the direction control valve, pressure control valves and a flow control valves very quickly. The problem is like this: the land in a spool valve separates two fluid passages. The land has a 25 mm length and 18.7325 plus or minus 0.05 mm diameter, meaning it is upper and lower limits I mentioned here, and operates in a 18.75 plus or minus 0.01 mm bore. Again, upper limit and lower limit for the bore is given. Assuming that the spool is concentric, the pressure drop across the land is 20.68 megapascal. Calculate the leakage flow rate past this land for nominal, minimal and maximal leakage conditions, assuming a fluid nominal, minimum and maximum viscosities of 32.1 mm square per second, 5.84 mm square per second and 800 mm square per second. Kinematic viscosity CST is given. So, solution how to do it? The nominal height of the passage is achieved when both the spool and bore have their nominal dimensions, because the nominal height means what? Here you will see 18.75 divided by 2, correct? Here you will see, friends, you will take directly the bore is 18.75, spool is minus 18.7325 by 2 is a nominal height or a clearance when I am considering the nominal dimensions. This is given by 0.00875 mm. So, the minimum height of the passage, meaning I am taking the lower limits now, the minimum height of the passage is achieved for the maximum diameter of the spool, correct? 18.7325 plus upper limit 0.05 is equal to 18.7375 mm, and minimum diameter of the bore is here 18.75 minus 0.01 and is given by, same here what I did here, I took here 18.74 minus 18.7375 by 2. Here I am getting 0.00125 mm. C minimum it is. Similarly, C max we have to find out. What is that? Maximum height of the passage is achieved for the minimum diameter of the spool. Minimum diameter is, you will see lower limit here, and the maximum diameter of the bore, and is given by same 18.76, correct, minus this 18.7275 by 2, because it is a clearance. This is given by 0.001625 millimeter. So, now viscosity, as I have told you, it is given in the CST, kinematic viscosity. I am converting into centipose by multiplying with the specific gravity of the fluid, assumed to be 0.9. I am converted here. Then I am converting into SI unit, Newton second per meter square. Newton per meter square is a Pascal and second is a S, I am writing here, Pascal second. I am converted here. How to convert? After getting this divided by 1000. Then leakage flow rate is given by, already we know that, pi dc cube by 12 mu delta p by L. You will remember very easily, pi dc cube by 12 mu delta p by L. Substitute all the values for the nominal height, for everything you have to find out. For the nominal height, what is the leakage? Minimum height, what is the leakage? Maximum height, what is the leakage? Already we found out in the previous slide, I have shown you how to calculate the minimum height, maximum height, nominal height. I am substituting here a nominal height here. Then only changes is here these two terms, viscosity and this, correct. Now I will get the QL equal to 9.414 into 10 to the power of minus 7 m³ per second. Similarly, the leakage flow rate for the minimum height of the passage, here it will change again. Minimum height as well as this will change. Then it will come 1.5088 into 10 to the power of minus 8 m³ per second. Similarly, for the maximum height of the passage is given by same, substitute the C will changes and this will changes, meaning dynamic viscosity will changes. You will get here 2.199 into 10 to the power of minus 7 m³ per second. Very simple, friends, it is. Only thing you have to remember the leakage flow, then possible to find out for the nominal diameter, minimum height and maximum height of the gap. I will show you one more. A cylinder with a bore diameter of 70 mm and a rod diameter of 31.25 is to be used in a system with a 45 liters per minute pump. Use the graph here, the graph is given in the figure, which will shows the pressure drop across the flow in liters per minute. They are given the pressure drop versus flow characteristics for the different port configuration. You will see here, first one is when P connecting to A, P is connecting to B, this is the flow rate passing. Similarly, A is connecting to tank, B is connecting to tank, middle one. Top one is, as I have told you, P to T, because it is a tandem neutral. Tandem neutral means P is connecting to T in the middle position. A and B are blocked. Then parallel configuration, crossed configuration. You are seen already this. Okay, now this for this combination you have to determine. P is connecting to B, A is connecting to T, meaning a crossed configuration, meaning it is retracting. Correct? For this, now what we will do? The flow from P to B, correct? P to B means pump is connecting to B, meaning rod end, it is correct. So this can be read from the graph, pressure drop versus flow. How to read this, friends? It is here, you will see here, the what are the bore diameter is given, rod diameter is given, then here the flow 45, you will see here 45 liters per minute, you will move up. I want to get from the, what is that? P to B, how much? P to B, how much I will get here? You will see, friends, 45, I will get here approximately 3.2 approximately for the port configuration of P to A, P to B, here down curve. Next, this is a configuration as I have to P to T, A to B. Now they are asking for the crossed configuration. They may ask for this also. Now you will see the pump flow is connecting to the tail side or a rod side. The head side is connecting to the tank. So the flow from the, see here, A to T, how it is? A to T is the return flow out of the blind end. This flow rate is greater than the pump flow, correct? Pump flow, what it is coming here, because area is very less, and must be determined by AP equal to pi by 4 dP square. You know the area of the piston. After substituting, I will get here. Then calculate the piston rod area also, dP square minus dr square, pi by 4. You will get 77 mm square, meaning I am finding out here piston area and the rod area, this area, this area. Then so the return flow here, return flow is given by Q pump divided by AP minus AR into AP. Substitute all the values, I will get the return flow is 56.25 liters per minute. Using this, you have to find out the pressure drop. You will see now. Now the pressure drop can be read from the graph A to T, no? A to T it is correct. A is connecting to T. A to T corresponding to the flow rate, return flow how much it is? 56.25. You will see here, you will mark here approximately the 56.25 and you will move up, here move up, approximately I will get here 6.2, correct? 6.2 the pressure drop for the return flow. Very simple like this. How to read this you have to learn. Very, very simple. Whether it is a crossed configuration or here, you have to find out the same way. Third, quickly we will see one more problem. A pressure relief valve contains a poppet with an area of 4.2 centimeter square on which the system pressure acts. During assembly, a spring with a spring constant of 3200 Newton per centimeter is installed in the valve to hold the poppet against its seat. The adjustment mechanism is then set so that the spring is initially compressed to 0.5 centimeter for its free length condition. In order to pass a full pump flow through the valve at a pressure relief valve pressure setting, the poppet must move 0.30 centimeter from its fully closed position. Determine the cracking pressure, determine the full pump flow pressure, meaning it is a pressure relief valve setting. Then third one is what should be the initial compression of the spring in pressure relief valve if the full pump flow is to be 40% greater than the cracking pressure. Okay, as usual, it is a poppet valve it is. We have to find out the first cracking pressure, determine the cracking pressure. So, we know that the force required to fully close is the product of initial displacement and the spring constant, and is given by F valve closed, force required to close, K into S initial value. Initial value is 0.5 is given, therefore 3200 into 0.5, meaning 1600 Newton. This is the initial force required to close the valve. Now we can calculate the cracking pressure knowing the cracking force. The F cracking equal to P cracking into A poppet, area of the poppet. So, P cracking equal to F cracking divided by A poppet. Now, we will substitute the value 1600, area of the poppet is given, but please take care friends, all units should be in the same unit. All centimeter I am converting into the meter. Now, we will get here Newton per meter square, then it is nothing but 3.81 megapascal. Next one is full pump flow pressure, meaning the pressure relief valve setting. Here the force required to fully open is the product of final displacement. Final displacement means 0.3 plus 0.5 is nothing but the 0.8 full opening and a spring constant. Multiply these two, then I will get the F fully open. Fully opening the force is K into S fully open, correct, meaning 2560. Now, this force must be equal to the product of full pump resistance and the area of the poppet, meaning F fully open equal to P full open into area of the poppet. What you will do now? The P, the pressure of the full pump flow, F fully open divided by A poppet. Already we found out, already we know here 2560 divided by area of the poppet is known. Substitute, I will get here 610 into 10 to the power of 4 Newton per meter square, or what you will do, divide by the 10 to the power of 5, you will get the megapascal 6.10 MPa. This is for the pressure for the full pump flow. Next one is what should be the initial compression of the spring in PRV if the full pump flow is to be 40% greater than the cracking pressure. Now, initial compression of the spring is already we know that F valve closed K into L, meaning K already we know 3200 into L. Now, F valve closed equal to same P cracking into A poppet. Now, P cracking equal to F valve closed by A poppet. Substitute the value here. Here already know F valve closed is 3200 into L divided by area of poppet. After doing this, I will get here 762 into 10 to the power of for L. So, we know that the force required to fully open is given by the product of full pump flow and the area of the poppet, correct here. Now, P full pump flow same, F fully open A poppet. F fully open is given by K into L plus 0.3. We have to find out L now, that is what I am telling you. So, F fully open equal to K is 3200. Then I am simplifying this 3200 into L multiplied by this 960. Okay. Now, the pressure when full pump flow, which is given by F force by an area fully open and poppet. Substituting the value here, then after simplification, what I will get here 762 L plus 229 into 10 to the power of 4. We can now calculate the ratio of pump full flow pressure to the cracking pressure, P fully open, P cracking, correct, which is equal to their given condition 1.6. After substituting this is given condition, I will do the simple modification here, 762 L plus 229 by 762 L. This is how much it is, friend, 1 plus 229 by 762 L. This 1 will go this side, meaning 0.6. 229 by 762 is nothing but 0.3005 into L, 0.6. Then L equal to approximately I will get it 2 centimeter. A double acting cylinder is hooked up to reciprocate. The pressure relief valve setting is 120 bar. The piston area is 0.032 meter square and the rod area is 0.0090 meter square. If the pump flow is 0.0026 m³ per second, find the cylinder speed and load carrying capacity for the following, meaning for extending stroke as well as retracting stroke. So, quickly we list it out, the given data. The pressure relief valve setting is given as 120 bar is there given. I am converting to Newton per meter square by multiplying 10 to the power of 5. Now, the piston area, it is given in meter square, no need to worry, and rod area also given in meter, because Newton per meter square I am choosing, all units should be same. Please remember, friends. Then pump flow QP equal to 0.0026 m³ per second, all are in the same unit. You will see, friends, cylinder speed and load carrying capacity during extending stroke. Cylinder speed during the extension is given by VE QP by AP, head side, correct. QP is known, AP is known. You will get 0.08125 meters per second. Similarly, load carrying capacity P equal to F by A. Then F equal to P into A, meaning P into AP, correct. P I know 120 and AP I know. After this, I am getting here divided by 1000, you will get it 384 kilonewton. Similarly, we have to calculate for the cylinder speed and load carrying capacity during the retracting stroke, correct. Cutting speed during the retracting stroke, VR equal to QP by AP minus AR, correct. You will substitute all the value, I will get it 0.1130 meter per second. Similarly, load carrying capacity P equal to F by A, correct. The load carrying capacity, F equal to P into A. That is why I am doing P into AP minus AR. Substitute all the values. Afterward, I am getting 276 kilonewton. Correct? Very simple it is. Very, very simple. Substituting the value, you will get it. Fifth problem. The circuit shown in figure below has a cylinder with 50.8 mm in diameter bore and a 25.4 mm in diameter rod. The pressure relief valve setting is 170 bar. if the meter out circuit, because you will see here meter out outflow is controlled, meter out flow control valve is closed completely. You will see here, if the meter out flow control valve is closed completely, what will be the pressure be in the rod end? The piston diameter is assumed to be the same as a bore diameter. Quickly list it out. What are the given data now? The piston diameter is given dp 50.8 mm. Always you will convert into same unit. The piston rod diameter dr equal to 25.4 mm. Convert into the meter. The pressure relief valve setting is given 170 bar. I am converting into Newton per meter square. Now you will calculate the piston area AP pi by 4 dp square. dp is given here. You will get it here. Similarly, the piston rod area you will calculate pi by 4 dr square, friends, substituting the value directly. Please note, the pressure in the blind end will be the pressure relief valve setting. Now calculate the piston force in the forward direction. So, the forward direction FP into AP, correct? I am substituting the setting pressure and area. I will get Fe equal to this much Newton divided by 1000 will give you the kilonewton 34.4386. Now, you will see this force is then applied over the smaller area on the rod area. Rod area is AP minus AR, correct? Now, calculate the pressure in the rod end as PR equal to Fe by AP minus AR. Substitute the value here, whatever I am getting here. Now, you will get how much it is? You will get here in bar I am getting 184.70796, which is the, you will see here, friends, pressure in retraction is 184.70, but maximum pressure setting how much it is? 170 into 10 to the power of 170 bar I am setting, but in return how much? 184.70, which is a very high, which will lead to wear and tear of the rod area seals. So, here please note, if the flow control valve on the rod end was inadvertently closed, the pressure in the rod end will be significantly higher, what I am calculating here 184.71 bar, than the pressure relief valve setting 170 bar. This can cause a damage to the rod end seals on the cylinder, which may create a dangerous situation. After knowing some of the problems, very simple problems, if they will give the any unknown data, how to derive the known data, I told you in the some problems in the today's lecture. We will conclude. Today we have discussed in detail the leakage flow through the spool valve, which is very important. Simple numericals on DCV, PCV and FCV. Okay friends, we will stop now and see you all in the next class. Until then, bye bye. Thank you one and all for your kind attention. Sarve jana sukhino bhavantu.